Some dog walking car was trying to pull in, and they were really unhappy at me. They were like, and I was like, I literally did this. I was like, please let me park here. I had to move. But yeah.
Well, I'm glad you did it.
Yeah.
Good done.
It's over. So over.
Never again.
Yeah, never again.
Where are you living then?
First and Red. It's like right across the street from the dog park.
Alone.
Yeah. It's a nice place. It's just a little dusty. And
Is it like in the back somewhere? Is it like a dark place?
it's like shrouded by trees.
You get a lot of light.
We do not get a lot of light.
Do you have a bedroom that's like here and then like a room here and like a bathroom here?
I don't know.
I like lived in it, like 2 Airbnbs there and
Ooh.
on that street. Is it like you have to walk through a driveway to get to the house?
Great
No.
recollection of your Airbnb experience.
Our house is literally the one on the corner of First and Red. Like
No,
literally.
this Airbnb was so terrible and I paid so much money for this Airbnb that was just like awful. And that's how I remember
Yeah,
it.
when I first visited Berkeley, like the year before I came here, we stayed in Airbnb in Oakland, and there was someone who was just having like a mental crisis, like under us in the duplex every night at like 2 a.m. Every night we just hear like pounding and like screaming at like 2 a.m. and there was no sleep that entire like trip. So I was like, cool, this is good.
Very cool.
Yeah.
This place I stayed in, this is before I had permanent housing, and I was just like moving between Airbnb, and it charged like 4K a month, and it was just like completely like
Like a
very, it was a full house, but it was just like it was very old and like things were just like falling apart. Yeah, it was just like I can't believe I can't believe that you can just like make money like this with such a
Yes.
crappy house and rent it out for so much money.
So the backstory for ours is like she has a coworker whose brother owns the house, who moved to SoCal, and like the house is just not being lived in. So they were like, we'll just give you the house for like this, in theory, below market price. But that below market price is still very high. So like, but my partner was like pretty convinced. So like, yeah.
Wait, what?
What?
Wait, what?
What?
Huh?
Which part? It's good. It's tough. It's nice.
You're just out a house,
It's not like given to us.
just out a tenant,
Yes.
just out a lease.
Yes.
Sorry, I heard that wrong. I was like, oh, you're given a house below market price?
We were given a offer to rent a house. It's sort of very different than being given a house.
It'd be great.
I mean, it is
Not
market.
that we were.
If the mortgage is
And that's Halloween.
that'd be pretty bad.
Right.
Finishing up some stuff this week, so.
Remember at the beginning of high school, they were doing like a border fuzzy lottery.
What's the word? Okay. That's
205,
that's pretty good.
and
Not a good
yeah, like, oh,
over.
I need to pull together a mortgage, but then we got it.
Where was your party?
Yeah, we're just on Friday.
I was really hoping to come, but there was like a lax event.
Like you cannot earn more money.
Yeah, but I think to sell it. Which makes sense, right?
Yeah, I guess that makes sense.
Yeah,
Then I was like,
sorry about
at the age of 21, I'm not ready for homeownership, so.
You know,
I should tell some of my friends who are just like literally bought houses so they could. Kind of like, yeah, but
Yeah, like, oh, that's crazy.
sort of like, but it's also Latin. We ended up 19 styles and they're like 11%.
Okay, folks, so let's start. It's, yeah, it's right time to start. So my goal today is to give a basic introduction into Datalog. And I know that some of you know Datalog very well. So this is not meant for, and on Zoom, people, if you don't hear me well, just speak up because I'm going to be pretty far away from the computer. So if you don't hear me well, let me know. Okay, so let's start by recapping what query languages we have considered so far. So we have considered first of the logic, which uses connectives or not exist and so on. And we didn't look much into this because it suffers from Trachtenbrot theorem. So static analysis is not so decidable there. But we looked at fragments, unions of conjunctive queries, which have and or no negation and only existential quantifier. And a further restriction, just conjunctive queries, which are just conjunction and existential quantifier. The problem with these languages is that they cannot express some very simple queries that are computable easily in polynomial time. But they cannot express them because of the limitations of logic, of the declarative nature of logic. And the two queries that you should know that they cannot express are two of them. So one is given a graph E of x and y. So I'm representing the graph using a binary relation E. Compute the transitive closure. Compute its transitive closure. It's kind of or should I put it, a famous query that cannot be expressed in logic. So what is a transitive closure? It is a relation T of, let's also call it x and y, where x and y is true if there exists a path using the edges in E from x to y. So we start at x, we continue with the second node, the third node, the fourth node, no matter how many nodes until we reach y. Yes.
Is the restriction here that the query is finite?
The restriction is that the query is finite. Yeah. There are, yeah, so let me get back to that in a second. So this is one famous query. The second one is even simpler. Given a relation, unary relation, just R of x, check if R is even. Check if the cardinality of R is even. Very frustrating. In first order logic, you cannot check if a relation has an even number of elements. How do we prove this? Well, we didn't delve into this in this class, but it's one of the possible topics for you to pick for the presentations. They are proved using related but different techniques. The first one is proved using Ehrenfeucht-Fressé games, EF games. And the second one is proved with a related technique called Pebble games. Once you see them, you cannot unsee them. They're that simple and clear. So strongly recommended that you learn about this. So Datalog fixes the first problem. It doesn't fix the second problem. And it's a major open question how if you can fix the second problem in an interesting way. So let's talk about Datalog. So it was introduced around early 80s, early 1980s, as a restriction of Prolog. So how many people here know Prolog or heard about Prolog? A small number. It was a language introduced even earlier that promoted using logic as a basis for programming languages. It had a procedural semantics that makes it very hard to understand what you're doing. There is the famous cut operator, which it takes an expert to understand what the cut is doing. Datalog said let's use the principle of relying on logic, but design a language specific for data, for computing on data. Prolog computes top-down, Datalog computes bottom-up. Major difference. So since it inherits from, then there is a second intellectual, how should I put it, lineage to Datalog. There has been a lot of work in the mathematics community, in the model theory community, in the 60s and probably earlier in the 50s on extending logics with fixed points. With the ability to write like inductive principles in logic. These are logics about over infinite domains, and I'm not very familiar with that line of work. For Ken Colaitis, who's here at the Institute, he knows that work pretty well. But that line of work influenced later on some of the theory developed about Datalog, because you can view Datalog as a restriction of some of those languages to finite structures. So since it comes from, it's a restriction of Prolog, Datalog, a Datalog program is a set of rules. And each rule, so a rule is exactly a conjunctive query, like here, like this one here. But so too much abstraction. Let's start with the first example. I'm going to show you how to compute transitive, how to express transitive closure in Datalog. So in Datalog, we write like this. X and Y are in the transitive closure if X and Y are in the edge relation. This is one rule. Second rule is X and Y are in the transitive closure if there exists some node Z such that X is in the transitive closure, and there is an edge from Z to Y. This is a Datalog program. It has two rules, and it computes the transitive closure of an edge relation. So you will recognize it. Look at the second rule. This is a conjunctive query. This is why I didn't want to use slides, because usually when I teach about Datalog, I spend a lot of time here dissecting the syntax of a conjunctive query, but you already know this. What kind of variable, how do we call the variables x, y that occurs here? What is the terminology? Head variables. These are the head variables. What happens to z? It's an existential variable. It's existentially quantified. We could put here an existential quantifier, but in Datalog we don't do it. It's pretty much like an Einstein notation. You don't write the existential quantifier. The Datalog rule needs to be safe. You cannot have in the head a variable that is not used in the body. And that's about it. These are really conjunctive queries. Often people, most of the literature on Datalog puts a comma instead of, this becomes a comma instead of conjunction. But I really prefer a conjunction. I'm not the only one, but yeah, several papers, they prefer a comma. Okay, so this is our example. Let's look deeper into how Datalog is evaluated. What is the meaning of a Datalog program? So for that, let's take a graph. And I'm going to draw this graph here. 1, 2, 3, 4, 5. And let's make it more interesting. Let's put a loop back. Yeah, so this is our graph, and the edge relation. How should I do this? Let me write it here. So the edge relation is a table with attributes x and y, or you can call them whatever. And it has all the edges: 1, 2, 2, 3, 3, 4, 4, 5. And 4, 2. So you should think about Datalog as repeatedly firing these rules and updating the relation key as it fires the rules. So initially, at the very beginning, T0 is the empty set. This is how Datalog starts, by computing the empty set. Then after the first step, let me put it here. After the first step, what is T1? So to compute T1, you reason as follows. We have two rules that compute T1. This means we take their union. There is an implicit disjunction between these two rules. So getting back here, Datalog is more like unions of conjunctive queries. It's not just conjunctive queries. So there is an implicit disjunction. So on the right-hand side, we use an old value of t. So what is the result of applying both rules to the old value of t?
Are you saying apply the first rule and then like until t, like for all the edges and then apply the second rule exactly once?
Yeah, you can apply the first rule first, the second rule second, but every time you apply a rule, it has to be on the original, on T0. So what if we apply T1, the first rule, what do we get?
All of E.
All of E. So let me write it here. It's going to be a little bit boring. So 1, 2, 2, 3, 3, 4, 4, 5, and 4, 2. Actually, I know how to speed things up. So this is T1. And as you wanted, we apply the second rule second. What do we get as a result of the second rule? This other?
Nothing.
Nothing.
Because, go ahead.
Because T is still the original one, is T0.
Why does this matter?
Why does it matter? What?
Like why is it not equivalent to just instead of using the empty set when you apply the second rule to use T1?
It turns out it is equivalent, but this requires a proof because the semantics that we are going to adopt always uses the previous version. If it didn't, then we need to worry about the order in which we apply these rules. This might matter. It turns out it doesn't matter. But you know, we want to start with a simple definition and prove later that these optimizations are possible. Yeah. So this is T1. T2 is computed in exactly the same principle. We use T1 on the left-hand side of the right-hand side of the rules. We fire them. So what is T2? The first rule says everything that's in the edge region. So I'm not going to copy it. I'm going to do something like this. Is there anything new that we add to T2? The first rule doesn't give us anything new. It's just the edge relation. But the second rule does. What do we get new from the second rule? Well, this T is T1. This contains all the edges. And here we join once again with the edges. So the pairs XY that are in this join can be described in English as pairs of nodes that are connected by a path of next to. And one edge from here, because this is just the edge relation for now, and another edge from here. So I can fill this out quickly. So it's going to be 1, 3, 2, 4, 3, 5, and that's interesting. So 4, 2, 4, 3, right? 4, 3. So plus everything that's above. Maybe I should delete this. So it's everything that's above plus this. 3, 2. That's 3, 2. Yeah, it's 3, 2 as well. Thank you. Let me try to do this event and put 3, 2 here. So here's 3, 5, and indeed 3, 2, and also 4, 4, 2.
4, 2 is in the first one, right?
I think it should be 3. Thank you.
Oh.
Okay, and this is how it continues. What is T3? This is where we start feeling frustrated. To compute T3, we fire the first rule again, and we again get all the edges. And we fire the second rule. So since the previous time we fired the second rule, we included all of T1 joined with E. Now we are going to repeat everything that we had here. But we do add more edges, more pairs. Which ones? Output length 3. Very good. So they are, so it's everything that's above, plus 1, 4. 3, 3, 3,
2, 5.
and did I miss?
2, 5, yeah.
Yeah, 2, 5. So let me put 2, 5 first.
2, 5, 2, 2. Wait, yeah, 2, 2.
So 1, 2, 3, 2, 2.
3, 3, 4, 3, 3, 4, yeah.
3, 3, and 4, 4. Okay, one more. So what is T4? Let me write it here. I hope you are lucky with T4. So now you got the principle. It's going to add to T3 all the paths of length 4. 1, 2, 3, 4. So it's going to add 1, 5. What about from 2? So 2, 3, 4, 3, 2, 3, 2, 3, which we didn't have. 2, 3.
We did have 2, 3.
We did have 2, 3. Yeah.
I think the only path of 1, 5 that we don't have is 1, 5 or 1, 4.
Good. That's it. I think you're right. So it's everything above plus this new node, plus this new pair. And T6, 55 actually. T5 will not add anything new. It's equal to T4. This is when Datalog terminates. You will also have 1, 4. You also have 1, 4. Or 1, 2, sorry. 2. Oh, you already have 1, 3. Yeah, never mind. Yeah. 4, 5.
Yeah, no, it's only 1, 5. Yeah.
Okay, so you get a sense how this is computed. It appears to be very inefficient, and it is very inefficient. There is a lot of redundancy. We'll come back to this soon. But it always terminates. That is the interesting observation. Even though we had a cycle, this does not cause any problems. The Datalog still terminates. If you're familiar with Prolog, the way I wrote it this way is because Prolog will not terminate in this program. It is left recursive. So when you ask it for the nodes X, Y that are connected, it will say, oh, I know how to do it. I'm going to look for nodes XC that are connected. How do I look for nodes XC? Well, I'm going to apply this rule again and try again T of XC. Prolog simply diverges on this program. Very frustrating. You need to reason about the internals of Prolog to write correct programs that terminate. Not so in Datalog. And Datalog is always every program terminates. Okay, so some terminology. E is called an extensional database predicate. Actually, I should say all the input relations are called extensional database predicate or EDB. T is called an intentional database predicate because this is something we are computing. Or IDB. So it's an old terminology, but it's now totally standard. So EDBs and IDBs. These refer to the predicates that are part of the input. This is our database. It can be indexed. We have statistics. The IDBs are what we are computing. Any other terminology before I move to semantics? No, I think I covered everything I wanted. Good. So now semantics. What is the meaning of a Datalog? Yes, Max.
This might be a silly question, but why the distinction between the EDB and the IDB? Because, we can of course emulate, the EDB with rules with empty
empty bodies.
Mhm.
And then, in more complex mentions data log, there's like, you can get into strata, which is like, well, there's not only two EDBs and IDBs, there's like this whole nested thing, so like, well, what was the original intention behind, EDB and IDB is like semantically meaningful.
Right, so how semantically meaningful is the distinction between EDBs and IDBs? And to be honest, I don't know the history behind this. There are many cases where it's blurry, what is an EDB and what is an IDB, and Max pointed to two of them, and one I actually want to discuss. But it's a terminology that you should know what it means, EDBs and IDB. EDB means the input relation that doesn't change, IDB means the thing that changes. Yeah, there isn't anything deep about this, just terminology. Max actually touched on a very important point. In logic programming, there is actually no distinction between the input predicates and the output predicates, because every tuple in the input data can be represented in Datalog as a fact. So in logic programming, there will be no stored database. There is nothing to index and pre-process, but instead the program is also presented with, let me write this here, with a set of facts that look like this. E of 1, 2 is true. E of 2, 3 is true. E of 3, 4 is true, and so on. 3, 4. This is an alternative view of Datalog, where there is really no distinction between IDBs and EDBs. The disadvantage is that with our database path, we don't have this stuff to optimize, or we don't have anything to index and to pre-compute statistics. Everything now is part of the program. It makes some proofs easier, but in databases, we do want to have this distinction between the data and the program. Yes.
We did something similar when we looked at like queries and homomorphisms, right? Because you can represent your whole database as just a conjunction of these specific, like, concrete tuple relation.
It's a good point. So we already saw this blurring this distinction between queries and tuples. Okay, so semantics. So you have seen gazillions of programming languages and recursive formalism, and each of them needs to come with a semantics. If you looked at Haskell, how many people studied Haskell? Haskell? Few of you. Well, the semantics is pretty much, I'm pretty sure it's the notational semantics. You get into these complicated square brackets. For Datalog, the beauty is the semantics is very simple. And actually, there are 3 different semantics, and they are all equivalent. So semantics 1 is a least fixed point. So it goes as follows. Let me denote, there is no good notation here. Let me denote with IDB. It's a set of IDB instances. So an example is needed here. So for example, IDB could be the set of power set actually finite subsets. Finite subsets of domain times domain. So we don't need this. Domain times domain. And this will capture our transitive closure example. So the set contains all possible instances of the relation D. And then we define, so definition, the ICO, immediate consequence operator. Again, terminology to remember here. Immediate consequence operator or ITO. Usually denoted T, if I remember correctly. So the P is a program, and P goes from IDB to IDB. And what it does, it takes an instance of the IDB relation. So I don't know who to call it, T, TD, T1D, T2D, and so on, and produces a new tuple of IDB relations. Now I really got lost here in the notation. T1 prime D, T2 prime D. By applying work rules. To the previous ID. To the input. To the input ID. It makes Datalog unfortunately so dry, because you have to write so much stuff. There is no standard notation. But the principle is very simple. This operator takes the current state of T, whatever set you're giving it, fires all the rules, produces a new set of T, a new T. This is all it does. And then the meaning of the Datalog program, definition, the semantics of B is the least fixed point, of the immediate consequence operator. So LFP stands for the least fixed point. So I think this requires a little background on the least fixed point.
Sorry,
Yeah.
fixed point in this case is the same as like fixed point, for example, like within the magical even something that just converges to it and doesn't like stays there, or well,
Yeah.
that's what I mean.
Yeah, it's even simpler.
But in our case, it would be like T4, for example. Like T4 is a fixed point.
Exactly. T4 or T5, whichever you want after T4. Yeah, but it's a good point. So let's reduce this more carefully. Remember that a partially ordered set is a set E with a partial order, where this is reflexive, anti-symmetric, transitive. This is a partial order. We always require, so in this lecture and many cases, we require P must have a minimum element. Which is denoted bottom. So the property is that for every x in P, bottom is less than or equal to x. Yeah, so we have a post set. They have some name when they have a minimum element. Sometimes they're called pointed, but I don't remember if there is a standard name. I'm not going to call them anything. Yeah, so we have any partially ordered set with a that has a minimum element. To give you an example, for example, the set of IDBs is partially ordered. How do we order two different IDBs? How do we order two instances of P? How do we compare them? Inclusion. You give me one instance and the second instance, I'm going to check that the first one is a subset of the second one. This is a partial order. Now, if a function f from P to P is called monotone, if if x less than or equal to y, implies f of x is less than or equal to f of y. And we are going to consider only monotone functions. So two definitions here. And it's fun to actually examine both of them. An element x is called a second. Want x? What do I want? Let's try x and z. X is called a prefix point. A prefix point. If f of x is less than or equal to x. Gets a little bit, if you start from bottom, it's bottom prefix point.
What's that?
Yes.
Oh, that means function.
Usually not, no, because you want f of bottom, you check if f of bottom is less than bottom. Who is less than bottom?
Not even big book.
Just bottom.
But doesn't F have to also map bottom to bottom because it's monotone?
No,
What is the answer to?
monotone just means that if you give me a bigger element, I'm going to return a bigger element. Yeah, so a prefix point is not what you get at bottom automatically. You might be lucky, and f of bottom is bottom, but you need to search for that least for the least prefix one. So and x is the x is the least fixed point. Let me call it different. Let me call it z. It's the least fixed point. If z is less than or equal to x for all the least prefix point, sorry. If this happens for every prefix point, prefix point x. Yes.
So if I think of like the image of P under F as a new poset or set, then the F of bottom would be the bottom of that like image poset, right?
Yes.
Okay.
Now you can think of it exactly where you have a poset and F kind of pushes it some. It doesn't have to push it necessarily up. So if this is your poset, pretty much like a lattice, this is bottom here. What F could do, for example, it could massage it into a small band, but there has to be a bottom. So it's going to map everything into here. F of bottom here, but you see it's above bottom.
Maybe this is where you're going, but are you going to say something about if f is something about if f is monotone, the prefix point is the least fixed point, or
The least prefix point is the least fixed point.
why is it not what isn't the prefix point also the least fixed point if f is monotone, or no?
It is. So if the least prefix point is the least fixed point.
So there's only one.
I'm saying like getting rid of least though. Like why isn't just the prefix point also the least fixed point if f is monotone?
It's not always the case. If you have you can have a prefix point where f of x is really smaller than x. For example, you start from here.
Oh, I see. I see.
And we map somewhere here.
So monotone. Oh wait, monotone can. Oh, I forgot that. All right.
Yeah. So the second definition is that x is a fixed point. If f of x is equal to x, and let's call u is the least fixed point. In general, it is not clear that the least prefix point or that the least fixed point exists. Yeah, but here is the little theorem. I wonder how much space I should use with this. It was meant to be a short detour, but it's a fun detour. So there is a little proposition. if Z exists, then U exists, and U is equal to Z. If there is a least prefix point, then that is also the least fixed point. And the converse usually doesn't work. I mean, in complicated sets in mathematics, you can construct examples where you have a least fixed point, and there might be this, which is also a prefix point, but there is no least prefix point. Okay, so getting back to our definition, the immediate consequence operator is monotone. Look at what the immediate consequence operator does. It takes a state of the IDP and returns E, union the join of that state with E. Okay, so question to you. You seem to like F to map bottom to bottom, because then bottom is the least fixed point, the least prefix point, and we are done. Getting back to this, to the immediate consequence operator of this program, does it map bottom to bottom? It maps bottom to what? To E. This is F of bottom. It's T1. Yeah, so we need to apply it again and again and again. Usually under marked conditions, what happens is that you can define this sequence. So you start from, let's call it U. Okay, U0 is bottom, and U T plus 1 is F of UT. And then this forms a sequence which is increasing. And if at any point you get a fixed, you get equality, you have U equal to UT plus 1, then this is a least fixed point. If you go to infinity, then you could consider taking the least upper bound, and you know there are things you can do in mathematics. But in Datalog, we always terminate, and that's what I want to solve. Okay, this is a little exercise for you. Try to prove this. It's a fun exercise. It is 2 or 3 lines. Prove that if the least prefix point exists, then that is also the least fixed point. And the converse is more difficult to disprove. Good, so this is the first semantics. We want the semantics of the program to be the least fixed point. And associated to this semantics is a simple algorithm that computes computes the answer, the output to a Datalog program using this principle here. So it's called the naive evaluation algorithm. Again, a standard terminology. Naive evaluation algorithm. So I'm going to describe it abstractly like this. Initially, all the IDBs at time 0 are empty. This is a little bit an ambiguous notation. What I mean is that if you have multiple relations that are IDBs in your program, all of them you set to the empty set. And then repeat. For t equals 0, 1, 2, and so on, we do the following. IDB at time t plus 1, it's going to be the immediate consequence operator applied to the IDB at time t. And t is okay. And if they are equal, of t plus one is equal to idb of t, then x is. Very simple and naive algorithm. Yeah, and this computes the least fixed point in this period. Question: what is the runtime of that algorithm? If you apply this to a Datalog program, to this Datalog program, and your relation E has n tuples. So let's write it here. So if E has n tuples, then the time of this algorithm is how big? Kind of the worst case runtime. Exponential in n, 2 to the power n. Let's revise this. How do we compute the immediate consequence operator? What do we need to do to compute the immediate consequence operator? We have two relations, E and E.
Memory all paths that are length and then add one more edge.
You could do it, but you know, you put your database hat, and what kind of operator do you recognize here? It's a join. And what kind of operation do you recognize between these two? It's a union. Yeah, so it's a join, it's a projection, and a union. So why don't I write this down here? The immediate consequence operator, TP, is E, union a projection of T join E. So what is the complexity of computing this once? Well, we know how big E is. It is n, but how big can T be? How many tuples can we get into T? So E has n edges. How big can T grow?
Whatever the credit number of these points.
Yeah, can it be exponential?
Yeah. Wait, maybe not actually. No.
No, because it terminates.
Yeah, so like worst case n, yeah.
What can we put in T?
And at most
It's most how many?
like n squared.
N squared.
Okay.
Yeah, at most all pairs of nodes in the graph. This is all we can do. This is at most n squared. This is at most n. So the most naive join algorithm, you know, it's n squared and the n cube if you really do it badly. Let's put n in here. But you can do it much. You can do much better. This is just one iteration. Now the big question is, how many iterations do we need? How many iterations do we need for this program?
Almost n.
At most n. At most the diameter of the graph. Yeah, because we grow and grow and grow. But once we reach the diameter of a graph, everything that wanted to get into that transitive closure is already there. Yeah. So the number of iterations is at most n squared. So the runtime.
Wait, number of iterations at most n squared?
Should be n. N is better. Yeah, and this is very wrong. Yeah, so if you do a careful analysis, it's much smaller. I wanted to not create any controversy. Yeah, I wanted an upper bound because the runtime is not exponential. It is in polynomial time. It is in p time, and we can discuss the exponent. It actually is not very well understood what the exponent is, but it's not exponential. Interesting. Let me write this down as a theorem here. So theorem, Datalog is in polynomial time, data complexity.
You would even do better, right? Because you could argue that like it's at worst n cubed. by saying that there are at most n squared things that could be in T,
Mhm.
and then each iteration will add at least one.
Yes.
Oh wait, that's still end of the fourth, so it's not, oh
It
wait,
depends on your program, right?
yeah.
Yeah, it depends a lot on how you write. It depends, so these are edges, if all the nodes are this, it depends on many things.
There are P complete data log programs. Too.
There are Datalog programs that compute a P-complete problem. The complexity classes, they don't distinguish between the exponents that we use in theory. For this, you need fine grained complexity. Okay, so this is a general statement for any Datalog program. You look at your IDPs; they can have many, but the arity of the IDPs is fixed, is given by the schema of the program. You look at your input database, the EDBs, they have only n distinct values, like the active domain. So therefore, the number of tuples you could potentially include in the IDBs is a polynomial. It's n to the arity of that IDB. And since at each iteration you have to include create some new tuples. It means that after a polynomial number of iterations, you have to stop. There is nothing more to add, and this is when you stop. Very cool. The second semantics, I'm already going to stop at the second semantics, but it's important to see that as well. So where did I write it? Semantics 2. Is as a minimal model. So what happens here is that we convert the program P into a sentence. And let me write it by some. As follows. I'm going to show you by example. We take the first rule and we put an arrow and we universally quantify. So the first rule becomes this. And the second rule becomes this for all x, for all y, and for all z, t of xy must hold if txz and t dx dy. Does this remind you of something? A rule like this, we have a name for it. Called the TGT, tuple generating dependency. This is exactly tuple generating dependency. It's a full one. There is no existential quantifier in the head. This is Datalog. Datalog are we can think of it as being tuple generating dependencies that are full.
Okay. Can you convert that to an existential? Like Z doesn't have to be for all, right?
Z doesn't have to be for all. Where do I need to push the existential?
Oh, right.
I push it here.
Hmm.
Yeah, and, remember we discussed it. There's a huge distinction between having an existential quantifier in the premise, which we can always pull outside and make it universal, or having an existential quantifier here. That creates a full.
The row directional is reversed. I think I got here.
Yeah, we got it. Yeah. I wanted to be consistent. Okay, okay, so then we are given. I'm going to make it specific to that example. So given an instance of the EDB, we call an instance of T a model. If the combination of E and T satisfies the formula phi B. So what is a model? Intuitively, is any relation T for that together with our given set of edges satisfies these two formulas. And then the semantics by definition, so the semantics is the minimal model. TD. So here, if you look carefully, the minimal model is the least prefix point. Because what we want to say is that if you apply this rule, if you compute the body of this rule, that must be contained in T. Doesn't have to be equal. So we are within this framework. The rule must be subset of the head. That's a note. And this is the least prefix point. But now we know that they're equal. You still need to prove it, exercise at home, but they are equal. Looks nice that we have two different semantics. Now, question to you: why do we need to insist on the minimal?
Because otherwise we take T to be the entire set.
Exactly. So here, for example, if we don't insist on the minimal, you could take T to be the set of all the 25 pairs of nodes. That is that is definitely a model. Is it also a fixed point? That's an interesting question. Yeah, it is a fixed
We
point.
did a lot, right? Because there's implicitly a T equals T, or no?
No, there is no such thing. So we have to see if we apply these rules to T being the set of all the nodes, do we get those nodes? I don't know. Pairs of nodes.
You basically only want the tuples that you have a proof that it should be in the set, right? Based on the rules. Like if you treat them as like inference rules, every tuple needs to have a inference rule or like a sequence of inference steps that can lead to that tuple, right?
Yeah, what you're describing is a property that we derive from from having the minimal model or the least fixed point. But the interesting, I mean, I find it interesting discussion is what happens if I look at a model which is not the minimal model, it's some arbitrary model. And for example, if you take T to be the set of all the pairs, that is a model because you don't need to think too hard. T consists of all the pairs XY. So no matter what is in E, it is in T. No matter what the joint produces, it is in T. So clearly that is a model, and we don't want that. I can't immediately answer the question, is it also a fixed point? It's not a
No,
fixed
right?
point.
Because 5 to 1 go, if you have 5,1, it goes nowhere. Because on the first step, yeah.
Okay, so you're saying I will not get 5,1. I definitely don't get it here. To get it from here, I think you're right.
But because the first step when on T0 is like all zero length paths, and then every time I evaluate the query, I like the first rule gives me all one length paths, and then my inductive hypothesis is like I have like all paths inside T. I have all paths of length like n smaller. So
You're still thinking about this progression.
yeah,
please.
yeah,
But it's not. We're not doing this.
yeah,
We are starting from the set of all pairs.
yeah. I agree.
Okay.
But I'm saying that
Wouldn't it violate monotonicity if you lost some things after applying?
no, but monotonicity isn't saying that I always get bigger. It's if I have a bigger starting point, then I get a
Yeah, so you're touching about a different property. I think it's called inflationary order. I'm going to write it here.
yeah, I got confused with that earlier too.
So F is called, is it inflationary? Expansive. F is expansive if x is less than or equal to f of x for every x. So you have the impression that the immediate consequence operator is expansive, but it's a wrong impression. It doesn't have to be this way. What happens is that the following holds for this sequence that we construct like this. It holds that that ut is always less than or equal to f of ut. And this requires a proof. How do we prove this?
Induction over that.
Induction, but I prefer to look here. Why does it hold here? Why is u0 less than f of u0?
Because that's you want.
Because it's bottom.
Yeah, because u0 is bottom. So this is less than f of bottom just because bottom is less than everything.
Yeah.
Why is u1 less than u2? Sorry, why is this less than f of bottom?
Monotonicity again, right?
This is where we use monotonicity. Bottom is less than f of bottom. We have already proven this. And now if we apply f, then we remain this relation. Repeat this, and this follows by induction. If this holds, then we apply f, and we get that f of u of t is less than f of u of t. This is u sub t plus 1. And this is f of u of t plus 1.
So if you take the full set that we're talking about and you repeatedly apply the consequence, do you end up with like the greatest fixed point or something then?
I have no idea. This is what I want to do with you. So I want to check what happens if we take t to be the everything. We can never decrease too much. It has to be stabilized. That's my intuition.
I think 5-1 that also fails, right? Because one never, if you want 5-1, then you need 1 to be y. And but there's nothing, one never appears on the right hand side of any edge. So
Okay,
here's,
so you want to check if 5-1 can be a t.
yeah.
So this needs to be 5, this needs to be 1. This is you're right. There is nothing here. End of the story.
Aren't we unioning H immediate consequence stuff though? Like we're not showing away the passive length 2 and we can do the passive length 3.
We are because like we keep adding the path of left 1 into t with the first step.
Yeah, again, the exercise is the following. So t now is the entire relation. How should I write it? 5, the set 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. And the question is, what is the immediate consequence operator of this t? There's nothing to do with our iterative process. It's just a way of checking whether this is a model, whether this is a fixed point. And the observation is not a fixed point. It is not a fixed point because at least 5-1 is missing.
I think
Doesn't our immediate consequence operator see monotonic?
It has to be, it is always monotonic because
Wouldn't this be violating monotonicity? Because if we give like something t in this case is as big as it can be, but it's giving us out a smaller set.
does it violate
The
monotonicity?
problem is you need to have something else that you give to t that then is smaller, but is like originally bigger. But this is like the biggest thing there is, so you can never have like another, it's like, oh, I see. That makes sense.
Very confusing. Monotonicity is what it says. Give me 2 elements. What is it? Give me 2 elements, and when I apply f, they still have to be in this order relation. What you are looking for is this expansive property. That if you apply f to and some x, you want to get something that is above x. That does not follow from monotonicity.
But I guess it's not, I think if I apply t to t or the immediate consequence operator to t where t is that, I'm not going to get t5. Because I'm going to get like, I could get like.
Is this one? Sorry, what you want to do?
He's saying that applying the immediate consequence to the full set does not give you the least fixed point immediately at least.
Oh, yeah, I don't claim it, you get the least fixed point. I have no idea what you're getting. Actually, if you start from the top, because this is what we do here, I think we get the greatest fixed point. Because you start from the top now, and you go backwards. You get U1, U2, and at some point you stop at the greatest fixed point.
So are not all data log like rules are, it's not necessarily monotonic.
Data log rules, the pure data log rules are always monotonic. Because we do not allow negation. We only allow conjunction.
Okay, I see.
Is there an interpretation of the greatest fixed point in terms of like data log or some kind of other?
Not as far as I know in data log, but there are interesting mathematical concepts and using computer science where the greatest fixed point makes a lot of difference. By simulation or stable coloring, they are greatest fixed points. Greatest yes.
Sorry, I meant to say data log rules are not always expansive, but they are always monotonic.
Exactly.
Okay.
And usually people ignore this. They ignore the fact that they are not expansive because we never get out of this limited framework where that word. This one here.
Because monotonicity is all we need to do this induction.
Exactly.
Okay.
We never leave this sequence. But if you do, because you want to extend data log, you want to add differential quantifiers, we want to add negation, then we need to be careful because all these bad things around it happen.
And I think it's especially confusing because it's tempting to think about TP as expansive because in most implementations, the way you implement TP is by sort of unioning back with what you have so far, which is sort of obviously expansive, right? And so you could turn any TP into a sort of inflationary TP by unioning with the input. And that's how implementations tend to work, but it's not necessarily experiment.
It's a very good point. Yeah, so actually, even if you add negation to data log, one way to make sense out of it, because now it's no longer monotonic, you just union with the previous state, and that is called the inflationary fixed point. And I hope we discuss this next week. But I still want to show you a few important things. So let's bring it back here. So the first discussion that I want to have is on the following. This was our single data log problem that we discussed before. Let me show you an alternative way to compute transitive closure. The same E of xy, but instead of left recursion, we can do right recursion. Yeah, so we have left recursion and we have right recursion. No big difference. But here is another way to do it. So the first result is always the same. We can do what's called a nonlinear data log, which goes like this. This is a nonlinear. So what happens here is that we define the transitive closure to contain all the edges. And then if Z is in the transitive closure and ZY is in the transitive closure, it means we have a path from X to Z, a path from Z to Y, then we have a path from X to Y. And my question to you is, think about a graph like this one. Can you tell me exactly how many iterations does the first data log program need in the naive evaluation? How many does the second? How many does the third? In terms of properties of the graph, yes. And now I wanted something more precise than n. What feature of the graph controls exactly the number of iterations?
Diameter.
The diameter of the graph. Very good. The diameter of the graph controls this. The diameter is the longest distance between any two nodes. What about the nonlinear one?
Longer diameter?
Log of the diameter. So it needs fewer iterations. It's very attractive. But this is not, unfortunately, this is not the end of the story. Although it needs fewer iterations, it ends up doing more work. And I think it's an important point, so I should show you this why this happens. Think about a graph, which is a chain, all the way to n. And think, yeah, so you can see this this graph here, 1, 2, 3, 4, up to n, and we have an edge between the node I minus 1 and the node I. Think about the last iteration of, let's say, the first program and this program. That is an iteration when we discover the edge, the pair 1 to n. In how many ways do we discover it by the first program? And in how many ways do we discover it by the last program?
Can you think of it in terms of the size of the join as well?
Yeah, you can.
It's like,
1 and n. Very good. So here it is just one way. If x is 1 and y is n, what does z need to be for me to discover that 1n is in the transitive program? N minus 1. It can only be n minus 1. Yeah, so it has to do very little work in the last iteration. If there is a join, there is all the repeated work, but intuitively, for the new fact, this is the only work that it needs to do. What about the nonlinear one?
I see any of the nodes.
Sorry?
Any of the vertices will be the halfway pointer.
Then any G can be any intermediate vertex. So here the number of the time of vertices I discovered it once, and here I discovered it like I don't know n minus 2 something like this, n minus 2 times. And of course this accumulates over the computations. It's not clear. Nobody knows how to analyze this very well. But the rule of thumb is that the nonlinear one is typically more expensive. But it's really typically. Yes.
The bottom one feels like almost like Bellman 40 or like Floyd-Warshall. Is there a connection there?
Sorry, bottom
Like,
one.
It feels like Bellman Ford or like Floyd-Warshall in some sense.
Yeah, these are connected. So Bellman Ford is your all pair shortest path, which is pretty much similar to the last one.
Like intuitively, the second one being like a self join where the cardinality is like growing each time, whereas the first one, the E is never growing.
Yeah, that's one way to think about this. The first one, E stays put, and only T grows, so you can take advantage of this. Okay, so I wonder, let's also go over the semi-naive because that was my plan. We go much deeper if we have a whiteboard discussion. And it takes much longer than I thought. So what we don't like about the naive algorithm is that at each step, it recomputes everything that is computed before, plus a new facts. So the semi-naive algorithm avoids this. Semi-naive algorithm will avoid this by keeping track of the delta of what was. Oops, it's not good for you.
I can move it.
Here.
We move the top.
Sorry.
We've been moving the laptop.
Ah, good, much better. So let me erase here. And briefly talk about delta. So delta of R tuples to be inserted. To be inserted. So the idea of incremental computation, and we had 2 lectures about this, is that we have computed a query Q that depends on R. We know its answer, but now we want to compute Q of R union delta R. And we don't want to recompute everything, so hopefully we can write this as the previous answer because it's monotone, So we know we need to add some stuff. And that stuff, hopefully we can compute it with a new query, which I'm going to write delta Q, but it's something we need to figure out what it is. But this new query can still look at R, but hopefully will exploit as much as possible the data. Okay, long story. Let me show you an example. Example 1, Q of xy is a join of rxe and scy. And I'm only interested in delta R. So what is Q of R union delta R and the old S? Yeah, so let me write here what I want. I want this to be the old version union. What is my delta Q? Yeah, I don't like how I wrote it. Let me write it like this, because you know what I mean. I want to find out the new tuples. What are the new tuples that I need to insert into R?
Delta R join S.
Sorry?
Delta R join S.
Delta R join S. Exactly. This is delta R of X and Z and join with S of Z and Y. Yeah, that's all I need to do. Here is a slightly more interesting one, and that's the only one I'm going to write. What happens if you have a self-join? X Z and R of Z and Y. What is delta Q in this case?
Delta R join with R and then on both sides.
Yes. So it is delta R XZ joined with the old R. And let me write it in Datalog style. So a second rule says you also have to insert R of XZ and delta R of CY. And are we done? No. What's still missing?
Delta R delta R.
Delta R. So there is a third rule that says we need to also add all the from the new tuples, so those that join with other new tuples. The R of Z and Z of Z and Y. Yeah, so these are the data rules.
We think about join as multiplication and unit as addition. This also falls out a little more nicely. You think about just distributing.
Exactly. This is exactly discrete differentiation, if you're familiar with it. And discrete differentiation, in standard differentiation, the derivative of R squared is of course just 2 times R prime. Yeah. So we should only have this twice. But this is not continuous differentiation, this is discrete differentiation. So we need this additional term. Okay, so semi-naive, I'm going to write it first in a way you always get confused when you try to derive a semi-naive algorithm. This is why I wanted you to get this picture correctly. The easiest way to think about this is that you start from this, but instead of computing directly the new IDB, you first compute the data. So I'm going to do this. So repeat T from 0, 1, and so on. We are going to compute the delta at time t is the difference of the IDB at time t minus IDB at t, and then just union them. IDB at time t plus 1 is IDB t union delta. And if delta t is empty, sorry, give me a second. Oh no, it's good. And if this is empty, then exit. if you write it this way, it's correct. Okay, it can't go wrong. All we did here is to pre-compute the difference. Then we added that difference to ITP. We got exactly what we had before.
Yeah.
But now the trick is that this difference is an incremental computation. And the reason is because the previous ITP itself was written as a union. Yeah, so we did into this expression, and this is actually TP of ITP T minus 1 union delta T minus 1 and minus ITP T minus 1 union delta T minus 1. Essentially the delta of this TP. And this is, of course, TP of IDP T minus 1 union the delta TP of IDP T minus 1 and delta T minus 1. And this is just your current IDP.
Wait, what happened to the minus union?
Yeah, I'm a little bit fuzzy here. We don't have to this. What I want to do, I want whatever I can get here, such that when I add it to IDBT, I get this. That's what I want. And it's the same meaning as here.
Yeah.
That doesn't have to be exactly the difference. It can be a superset of the difference.
Okay.
Yeah, so I think it will take me a little bit to get this right. But I wanted to present you with this way of thinking. Start with something naive, just compute the difference. And then remember that this is itself an incremental computation from the previous step. And this is how you get the semi-naive evaluation.
Is there a fully non-naive algorithm? Is that me?
I think Max is into this business of developing the non-naive algorithm.
Reddy's the person to ask, but you guys does have good examples of like instances in which the cinematic algorithm overcomputes. And they're sort of some I don't know much. Do you remember those, Dan? They're interesting cases. They're not super hard to spell out when cinematic is factual.
But one aspect that I really like about Datalog, and this underemphasized, is that because this fixed point semantics is so permissive, you could change the naive algorithm in many ways and still get the correct fixed point. For example, you might evaluate the rules out of order. Maybe you like, if you have multiple rules, you can, as somebody suggested at the very beginning, you evaluate the first rule, and then the result of the first rule you plug it into the second rule, and the result of the second rule plug it into the third rule, and you still get the same fixed point. People have applied this for distributed data log with message passing. So you create new tuples, you send them around, and whenever the new tuples arrive, you will create new tuples, and when nothing new is created, this is when you stop. You don't have to worry about the stages at t plus 1 and so on. Yeah, so avoiding the synchronizations is what Connors is. This is what keeps Connors awake at night. Good. So let's stop here. We continue with connection between Datalog and logic, and of course I want to show you descriptive complexity. Datalog with appropriate engagement can capture exactly polynomial time. With the difference semantics, it captures exactly polynomial space. So there are interesting things to know about Datalog. Good. See you next week, folks.
Does this third program and not linear?
Oh, sorry, we had some. Okay, so there were comments on
Robert one was ours. I'm pretty sure this isn't our, oh, they're on whatever.